Hello dear friends, welcome to my channels. Today's discussions is quantum field theory. So friends, you will check that I will discuss also harmonic oscillators. Yeah, in my video. I hope you everyone will watch, and you will see that you will see that harmonic oscillator quantizations and free scalar field, and you will also learn simple harmonic oscillators, free fields, real scalar fields, okay, Hamiltonian formalisms, Lagrangians. You have already watched, I hope. Otherwise, I will give the link in my channel link. You will get that the Hamiltonian formalisms. Okay, so friends, now I want to discuss that vacuum. Okay, now I want to discuss vacuum, because before that you see the delta function evaluated at 0. It has its infinite spike. Moreover, the integral the omega p bar diverges at large p. Okay, what to do? So let's looking start by looking at the ground state, where the infinity first becomes apparent. Okay, ground state. So ground state, so we start the vacuum. Following our procedure for harmonic oscillator, let's define the vacuum ket 0. Okay, bra and ket, it is ket 0, by insisting that it is annihilated by all AP. So that this equation is very important. AP ket 0 equals to 0 for all P. With these definitions, the energy E0 of the ground state comes from second term in H0 H ket 0 equal to E0 ket 0, okay, and dqp. Okay, so this equation, we use this equation is very important. This is the Hamiltonian equations, term in the Hamiltonian equation, second term in the Hamiltonian equations. So we get, because the H is equal to half into dqp 2 pi cube, and a beta ap p a conjugate plus ap bar this is these equations. From these equations we get h ket 0 e0 ket 0 dqp 1 half into omega p cap del cube 0 means Dirac delta functions, and ket 0 equal to infinity ket 0. So taking the limit where L tends to infinity, okay, the subject of quantum field theory is rife with infinities. Each tell us something important, usually that we are doing something wrong or asking the wrong questions. Let's take some time to explore where the infinity comes from and how we should deal with it. In fact, there are two different infinities lurking in the expressions. Lurking the expression, this is the given expression h ket 0 and E0 ket 0. The first arises because space is infinitely large. Infinities of the type of often refer to the infrared divergence, although in case the infinity is so simple that it barely deserves this name. To extract out this infinity, let's consider putting the theory in box with sides of length L, and we impose periodic boundary condition on the field. Then, taking the limit where L tends to infinity, we get 2 pi cube del cube 0 equals to limit L tends to infinity integration minus L by 2 into upper limit L by 2 to d cube x e to the power I x bar p bar, where p equals to 0 equals to limit L tends to infinity minus L by 2 and L by 2 d cube x equal to v, where v is the V is the volume of the box, and del 0 is the divergence arises because we are computing the total energy rather than the energy density epsilon 0. To find epsilon 0, we can simply divide it by the volume. Epsilon 0 is equal to E0 divided by V, and V0 means d cube d cube pi p, and 2 pi cube or half into omega p, which is still infinite. We recognize it as the sum of ground state energies for each harmonic oscillators. But epsilon 0 tends to 0 due to the p cap mod of p means momentum, energy momentum operator tends to infinity limit of the integral. This is high frequency and short distance infinity known as the ultraviolet divergence. This divergence arises because of our hybris, and we have assumed that our theory is valid to arbitrary short distances scales and corresponding to arbitrary high energies. This is clearly absurd. The energy should be cut off at high momentum in order to reflect the fact that our theory is likely to break down in some way. We can with the infinity in 2.24. Okay, so 2.24 means our equation is that the h ket 0 is equal to e0 ket 0 dq p half into omega p bar del cube 0. That equation ket 0 you have already seen that equation. These equations, friends, these equations, okay, these equations is, say any name, any equation name, 2 for 2 2 2 3 any equation. This equations is important in more practical way. In physics we are only interested in energy differences. There is no way to measure E0 directly, so we can simply redefine the Hamiltonian by subtracting of the infinity. H is equal to d cube p divided by 2 pi cube into omega pi a plus p bar and a p conjugates. Okay, so that we with this new definition h cat is equal to 0. In fact, the difference between the Hamiltonian and the previous one is more an ordering ambiguity in moving from the classical theory to the quantum theory. For example, if we define the Hamiltonian of the harmonic oscillators to be h is equal to half into omega p minus ip omega q plus ip. So friends, h is equal to half into omega q minus ip and omega q plus ip, which is classically the same as our original choice. Then upon quantizations, it would naturally give h is equal to omega, h is equal to omega a plus into a. Okay, product of a plus into a into omega, triple product. Okay, so this type of ordering ambiguity arises a lot of field theories will come across a number of ways of dealing with it. The method that we have used above in is called normal ordering. Definition: we write normal ordered string of operator phi1 x1 and phi n xn as phi n such that phi n x a phi1 x1 phi n xn such that it is defined to be usual product with all annihilation operator ap bar placed to the right. So for the Hamiltonian we could write as h equals to d cube p divided by 2 pi whole cube omega p bar a plus p bar into a p bar. Okay, in the remind of this section, we will normal order all operators in this manner. The cosmological constant. Next we discuss cosmological constant. Cosmological constant. Above I wrote there is no way to measure E0 directly. There is a big caveat here. Gravity is supposed to see everything. The sum of all 0-point energies should contribute to the stress energy tensors that appears on the right hand side of Einstein's equations. We expect them to appear as a cosmological constant. Lambda is equal to E0 divided by V. So R mu nu minus half R g mu nu is equal to 8 by g t mu nu plus lambda g mu nu. Okay, cosmological constant you also get Einstein field equation. Also you can check it in my videos where Einstein field equations I have already published in my videos. So you know this equation is well known for everyone. So current observation suggests that 70% of the energy density in the universe has the properties of cosmological constant with lambda proportional to 10 q 10 to the power minus 3 ev whole to the power 4. This is much smaller than the scales in particle physics. In particular, the standard model is valid at least up to 10 to the power 12 eV. Okay. So why don't the 0-point energies of these fields contribute to lambda? And or if they do, why cancels them to high accuracy? This is cosmological constant problem. No one knows the answer. So the Casimir effect. I'm using the normal ordering prescription. We can happily set E0 is equal to 0 while chanting the mantra that the only energy differences can be measured. But we should be careful, for there is a situation where difference in the energy of vacuum fluctuations themselves can be measured. To regulate the infrared divergence, we will make the x superscript 1 direction periodic with size L and impose periodic boundary conditions such that phi x bar is equal to phi x bar plus L n bar, with n equals to n bar is 100 unit vectors, and we have a yz, but remember that we should compute all physical quantities per unit area A. We insert two reflecting plates separated by a distance d less than equals to L in the x superscript 1 directions. The plates are such that they imposed phi x is equal to 0 at the position of the plates. The presence of that plates and affects the Fourier decomposition of the field, and in particular means that the momentum of the field inside the plates is quantized as p cap is equal to n pi by d py pz. N belongs to z plus. Okay, so for a massless scalar field, the ground state energy between the plate is this equation. Follow these equations, which at least naively depends on the naive guess it's true. It would mean that there is a force on the plates due to fluctuations of the vacuum. This is the Casimir force, first predicted in 1948, observed 10 years later. In the real world, the effect is due to vacuum fluctuations of the electromagnetic field. with the boundary condition imposed by conducting plates. Here we model the effect with a scalar. But there is a problem. E is infinite. What to do? The problem comes from the arbitrary high moment models. We could regulate this in a number of different ways. Physically, one could argue that any real plates cannot reflect waves of arbitrarily high frequency. At some point, things begin to leak. Mathematically, we want to find a way to neglect modes of momentum p less than greater than a inverse for some distance scale a less than is equals to d, known as the ultraviolet UV cutoff. One way to do to change the integral. Okay, so this is the e to the power. Okay, exponentials with multiply with exponential. Okay, now this is the multiply. We get these equations. Okay, which has the property that a tends to 0 0 regain the full infinite expression. These expressions we get from here gives us something we can easily work with. Of course, we made it finite in a rather ad hoc manner, and we better make sure that any physical quantity we calculate does not depend on the UV cutoff A. Otherwise, it is not something we can really trust. The integral this equation is doable but a little complicated. It's lot a simpler if we look the problem d is equal to l 1 plus l plus 1 sorry 1 plus 1 dimension and d is equal to 3 plus 1 dimensions. We will find that the same physics is at play this kind of equations. Okay, these equations play that e l 1 plus 1 d is equal to pi d divided by n equals to 1 to infinity. We now regulate the sum by introducing UV cut of a introduced above. This renders the expression finite following finite, allowing us to start manipulate it. Thus it does this way I get. Okay, en plus e1 plus d. Okay, this we get, where in the last line we have used the fact that a less than d. Okay, a is less than and is more less than d. We can now compute the full energy e11 u11 d u11 l minus d, these equations. This is still infinite in the a tends to limit a tends to 0, which is to be expected. However, the force is given by del E1 plus 1 divided by del D. Del D is equal to pi 24 d square plus, where the include terms of size d by L and a by d. The key point is that as we remove both the regulators and take a tends to 0, L tends to infinity, the force between the plates remains finite. This is the Casimir force square. If we plug through the analog calculation d is equal to 3 plus 1 dimensions and perform the integral, we would find the result. This result we can find the true Casimir force is twice as large as this due to the two polarization states of the photon particles. Now this is very interesting topic. Particle having dealt with the vacuum, we can now turn to the excitations of the field. It is easy to verify that H A plus P is equal to omega P A plus P and H A plus A P bar mass. These equations we get. Okay, so which means that just the harmonic oscillators we can construct energy eigenstates by acting on the vacuum Ket 0 with A plus P. Let Ket P is equal to A plus P. P means conjugate A plus P Ket 0. The state has energy H ket P and omega ket P and omega square P is equal to P square. Okay, this is the formula, but we recognize this is the relativistic dispersions relations for a particle of mass m and 3 momentum p. Square P is equal to P bar square plus m square. Okay, so now the number 24 that appears in the denominator one-dimensional Casimir force plays a more famous role in, in string theory. The same calculation in the context in the reasons the bosonic string lives in 26 equal to 24 plus 2 space-time dimensions. You will need to attend next term's string theory course to see what on earth this has to do with the Casimir force. Now we integrate the state P and momentum eigenstate state in single particle of mass m to stress this. From now we will write E P cap P bar and everywhere instead of omega P cap. Let's check this particle interpolation prediction by studying the other quantum numbers of Ket P. We may take the classical total momentum Ket P cap and turn it into a operator. After normal ordering, it becomes P vector is equal to these equations we get. Okay, you will see. Now, acting on our state, Ket P has momentum P. We learn that it is indeed a eigenstate. And P into Ket P, we get this equation P and Ket P is equal to P small p into Ket P, telling us that the Ket P has momentum P. Another property of Ket P that we can study is its angular momentum. Once, friends, we see that we can study is its angular momentum. Once again, we may take the classical expression for the total angular momentum of the field and turn it into an operator. J superscript I epsilon superscript I j k integration d cube x j superscript 0 and to the power jk. It is not hard to show that acting on the one particle state with 0 momentum j superscript I Ket P equals to 0 which we interpret as telling us that the particle carries no internal angular momentum. In other words, quantizing a scalar field give rise to spin zero particle, multi-particle state, bosonic statistics and Fock space. We can create multi-particle states by acting multiple times with A plus. We interpret the state in which n A plus s act on the vacuum as an n particle state. Okay, create P1 dot n vector equals to a plus p p1 vector pn vector and k 0. This is the equation, because all the a plus is continue among themselves. The state is symmetric under exchange of any two particle. For example, ket p comma q is equal to, this is the symmetric, okay, equals to q comma p. This means that the particle is Boson's particles. The full Hilbert space of our theory is spanned by acting on the vacuum with all possible combinations of a plus s equal to ket 0 and a plus p ket 0, a plus p a plus q ket 0, a plus p r k 0 dot 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 dot. This space is known as Fock space. Fock space is simply the sum of n particles Hilbert spaces for all n greater than equals to 0. There is a useful operator which counts the number of particles in given state in the Fock space. It is called number operator n. Capital N is equal to integration d cube p divided by 2 pi cube a plus conjugate a plus vector p and satisfies n p1 p n k vector and small n p1 p2 k vector. The number operators commutes with Hamiltonian n comma h equals to 0, ensuring the particle number is conserved. This means that we can place ourselves in the n particle sector and stay there. This is property of free theories, but will no longer be true when we consider interactions. Interactions create and destroy particles, taking us between the different sectors in the Fock space. Operator value distribution, although we are referring the state ket space ket p as a particle, there are no localized in space in any way. In any way, they are momentum eigenstates. Recall that quantum mechanics, the position and momentum eigenstates are not good elements of the Hilbert space, since they are not normalizable. Similarly, in quantum field theory, neither the operators phi x or ap are good operators acting on the Fock space. This is because they don't produce normalizable states. For example, inner product 0 and ap a plus p 0 p is equal to pp is equal to 2 pi cube del 0. Similarly, we get inner product 0 phi x vector 0 0 is equal to inner product x by x is equal to del 0. They are operator value distribution rather than functions. This means that although phi x has well defined vacuum expectations value 0, expectation value 0 phi x 0 is equal to 0, the function of the operator at a fixed point are infinite. Expectation is equal to infinity. we can we can we can construct well defined operator by smearing these distributions over space. For example, we can create a wave packet ket phi is equal to integration d cube pi p divided by 2 pi whole cube e to the power minus p x phi p momentum phi p and ket p, which is partially localized in both position momentum space. A typical state might be desired by Gaussian phi p is equal to exponential p square divided by 2m square. Relativistic normalizations. We have defined the vacuum ket 0, which is normalized 0 comma 0 is equal to 1, or we normalize as as expectation value of 0 is equal to 1, the one particle p is equal to a p0, then satisfy pq is equal to 2 pi whole cube the del q p minus q. But is this Lorentz transformation? P mu is equal to lambda mu nu p nu superscript nu such that three vectors transforms as p tends to p dash. In the quantum theory, it would be preferable if the two states related by a unitary transformation. Ket p tends to ket p u lambda ket p. This would mean that the normalizations of ket p and ket p are the same whenever p and p dash are related by a Lorentz transformation. By we have not been at all careful with normalizations. In general, we could get ket p equal to these equations. Okay, for some in unknown function lambda p comma p p comma p. How to figure this out? The trick is to look at the object which we know as Lorentz invariant. One such operator onto one particle states with normalizations. We know this is the given is equal to this equation. 1 equals to dqp by this equation. This operator is Lorentz invariant, but it consists of two terms. One is integration dqp and another project is p ket p and bra p multiply. Are these individually Lorentz invariant? In fact, the answer the Lorentz invariant measures is dqp into 2 e bar vector p dqp proof. dqp obviously Lorentz invariant and relativistic dispersion relations from massive particles p mu m square p mu into p mu m square is equal to this equation we get, and is also Lorentz invariant. And solving for p0 are two branches p0 plus minus ep, but the choice branch is another Lorentz invariant concept. So piecing everything together, the following combinations must Lorentz invariant: d to the power 4 del p square p dash square minus m square p0 greater than 0 is equal to dqp divided by 2p0 and p0 is equal to ep bar, which completes the proof. From the result we can figure out everything else. For example, the Lorentz invariant del function for three vector is ep del q p minus q, this is the, and which follows becomes dqp divided by 2ep and del cube p cube p minus q. And so finally we learned that relativistically ket p is equal to 2 ep into ket p is equal to this equation. Notice that our notation is rather subtly the relativistically normalized momentum state ket p differs from ket p vector by the factor root over 2 ep vector. These states now satisfy p by k q 2 pi cube this equation satisfies. So we get ap a plus p is equal to root over 2e ap plus we won't make use this notation here. Complex scalar field. Consider a complex scalar field phi x with Lagrangian L equals to this equation, and notice that in contrast to the Lagrangian for a real scalar field there is no factor of half in front of Lagrangian. For complex scalar field psi is equal to phi 1 plus I phi 2 root over 2, we get the factor 1 by 2 coming from the 1 by root 2 the equations of motions are these equations motions we can get these two equations of motions. Okay, I hope it is clear now. Where the second equations is the complex conjugate of the first, we expand the complex field operator as sum of plane waves as psi is equal to these two equation we get. And since the classical field psi is not real, the corresponding the okay, corresponding quantum field psi is not Hermitian. This is reason that we have different operators p and c plus appearing in the positive negative frequency. The classical field momentum is pi is equal to del L divided by del psi dot is equal to psi star. We also turn this into quantum operator field, which we write these two equation. Okay, you see these two equation. Okay, now the commutation relation between fields and momenta are given by, you see this is these two are relations. Next, together with other related by complex conjugation as well as the psi x and psi y is equal to psi x psi plus is equal to 0, one can easily check these field commutation relations are equivalent to the commutations relations for the operator bp and cp. You get two equations. Okay, this is the Poisson-Bracket, and get these equations also. So in summary, quantizing a complex scalar field gives rise to two creation operations b plus p and c plus p. These values are the interpretations of creating two type of particle, both of mass, both spin 0. They are interpreted as particles and antiparticles. In contrast, for real scalar field, there is only a singular type of particle. For a real scalar field, the particle its own an antiparticle. So we get Q is equal to this equation, and normal or ordering the wave equation quantum operator. This is the normal. Quantum operator is equal Q is equal to d cube pi divided by 2 pi cube, and c plus p vector and c plus b plus and nc minus nb. Okay, normal operator. Q counts the number of antiparticles and c minus the number of particles, and we have h comma q Poisson bracket, ensuring that the q is conserved the quantity in the quantum theory. Of course, in our field theory, big deals because nc and nb are separately conserved. However, we will soon see that the interacting theories q survives as a conserved quantity. So friends, we see that however we will soon see that in interacting theories Q survives as a conserved quantity while in C and in B individually do not. The Heisenberg pictures, although we started with a Lorentz invariant Lagrangian, we slowly butchered it as we quantized. Introducing a preferring time coordinate t, it is not at all obvious that the theory is still Lorentz invariant after quantization. For example, the operator phi x depend on space but not on time. Meanwhile, the one particle states evolve in time Schrodinger equation. I dp d ket p dt is equal to h ket pt is equal to ket pt is equal to e to the power I ept ket p. Things start to look better in the Heisenberg picture where time dependence is assigned to the operators O. OH is equal to e to the power, okay, DOH e to the power IHT, OS e to the power minus IHT, otherwise DOH divided by DT IHOH, pause bracket, where the subscript S and H tell us whether the operator is in Schrodinger or Heisenberg pictures. In field theory, we drop the subscript and we will denote the pictures by specifying whether the fields depend on the space phi x, the Schrodinger picture, or space time phi x t comma t is equal to phi x, the Heisenberg pictures. The operators in the two pictures agree at a fixed time, say t equals to 0, t is equal to 0, the commutations relations become equal to commutation relations of the Heisenberg pictures. This is the commutation relations. And now that the operator phi x is equal to phi x comma t depends on time, we can start to study how it evolves. For example, we have phi dot is equal to I h phi phi I by t d cube y pi y square del phi y square m square plus phi y square phi x equals to I into d cube y pi y. This equation you get. And now meanwhile the equation motions for pi dot is equal to these equations, and we get these equations, and where we have induced the subscript y is del subscript y when they may be same confusion about which argument the derivative is acting on. To reach the last line, we have simply integrated by parts. So we get clean Gordon equations. These equations we can get from the equation where we have included the subscript, okay, and the things are beginning to look more relativistic. We can write Fourier expansion of phi x and get these equations, which follows the commutations relation h a comma p e p, these equations. And phi x comma t is equal to d cube p 2 pi cube 1 by root over 2 ep ap, these equations. So p dot x is equal to, we get, which looks very similar to previous expansion, except that the exponent is now written in terms of 4 vectors. Note that the sign has flipped in the exponent due to our Minkowski metric contractions. It's simple to check, indeed satisfy the Klein Gordon equations. Okay, look this pictures figure. This is the figure 4. Okay, look this figure. Okay, you see O1 and O2. Okay, so causality, we are approaching something. Causality, we are approaching something Lorentz invariant in the Heisenberg pictures, where phi x now satisfies the Klein Gordon equation, and they are still hint of non-Lorentz invariant, because phi and pi just satisfy equal time commutation relations. This is the commutation relations equal. So, but what about arbitrary space-time separations? In particular, if for our theory to be causal connected, does our theory satisfy the crucial property? Let's define del x comma y equal to phi x comma phi y. The objects on the right hand side expressions are operator. However, it is easy to check by direct substitution that left hand side is simply a C number function with integral expression del xy is equal to d cube pi p and 2 pi cube 1 by ep, these equations. Okay, What do we know about these functions? It is a Lorentz invariant. Thanks to appearance of the Lorentz invariant measure dq divided by 2ep. It does not vanish for time like separations. For example, x minus y is equal to t comma 0 comma 0 gives phi x comma 0 phi x comma t, this equivalent to these equations: int imt minus imt plus imt e to the power. Okay, it vanishes space like separations, and the follows del x comma y equals to 0 and at equal times for all x minus 1 whole square less than 0, which can see explicitly by writing. So we get these equations. Okay, these equations is the commutator, and noticing that we can flip the sign of p in the last exponent as it as an integration variable, but since del x comma y x minus y is Laurent invariant, it can only depend on the x minus 1 whole square, must therefore vanish for all x minus y whole square less than 0. Now we discuss propagator. Okay, we therefore learn that our theory is indeed causal with commutator vanishing outside the light cone. This property we continue to hold in interacting theories. Indeed, it is usually given as one of the axioms of local quantum field theorems. I should mention, however, that the fact that commute phi x phi y is the C number and functions rather than an operator is property of free field only. Propagators. We could ask a defined questions to probe the causal structures of the theory. Prepare a particle at space-time point y. What is the amplitude to find it point x? We can calculate this. This is the expectations. Okay, this expectation, this value 0 phi x phi y and 0. Okay, this value is equals to these equations, means this is the propagator. So the function dx comma minus y is called the propagator, and for space like separation x minus y whole square less than 0, one can show dx minus y decays like this way: dx minus y proportional to e to the power minus m mod of x minus y. Okay, so it decays exponentially quickly outside the light cone, but nonetheless is non-vanishing. The quantum field appears to leak out of the light cone. Yet we have just seen the space-like measurements commute and theory is causal. How do we reconcile these two facts? We can rewrite calculation. This calculation we can rewrite. There are words you can wrap around this calculation. When x minus 1 y whole square less than 0, there is no Lorentz invariant way to order events. If a particle can travel in a space-like directions from x tends to y, it can just as easily travel y tends to x. In any measurement, the amplitude for these two events can cancel. And now you see with a complex field scalar. Okay, complex field scalar, this equals to 0 you can look the equation outside the light cone. The interpretations now is that the amplitude of the particle to propagate from x tends to y cancels the amplitude for the antiparticle to travel for y tends to x. In fact, this interpretations is also there for a real scalar field because the particle is its own antiparticles. The Feynman propagators. Feynman propagators is, as we will see shortly, one of the most important quantities in interacting field theory is called Feynman propagator. Feynman propagator is del f this equation, okay, and where t stands for the time ordering and placing all operators evaluated at later times to the left. So claim there is a useful way writing Feynman propagator in terms of a four momentum integral. This way I can write. And now notice that this is the first time in the course we have interpreted over four momentum. Until now integrated only over three momentum with P0, P superscript 0 fixed by the mass shell condition to be P superscript 0 EP cap EP vectors. The this equation for del f, we have no such conditions on P0 P superscript 0. However, as it stands, this integral ill-defined because for each value of p, the denominator p square minus m square m square is equal to p0 square minus p square m square whole square, and p superscript 0 is equal to plus minus ep root over p square plus m square. Okay, now you see the contour of the Feynman propagator. Okay, now let's start proof. Proof is that 1 by p square minus m square is equal to this equation proofs. Now you can write the residue. Now use the residue theory p0 u plus minus ep, and you see everything p0 tends to I infinity, hence x0 less than y0. We have the del f, del f xy. Okay, okay, del fxy is equal to dx minus y. Okay, in the representation is wrong. Del fx comma y is equal to dx minus y. Okay, just putting the values, and del fx minus y and del fxy, we get these equations dy minus x. And where to go the second line to the third, we have flipped the sign of p, which is valid since we integrate over dqp. All other quantities depend